Swayam Prabha. Digital India. Educated India.
Hello student, welcome back to the course on optimization methods for civil engineering. So in the last class we have solved some optimization problems, so mainly single variable optimization problem and multivariable optimization problem with constraint or without constraint using classical optimization methods in MATLAB. So in today's class we will solve the same problem whatever we have solved already using classical optimization methods. So those problems we will solve using GA and particle swarm optimization. So these two are two meta-heuristic optimization methods. So we will use initially particle swarm optimization PSO for solving those problems, and then we will apply GA genetic algorithm for solving those problems in MATLAB. Let us see the first problem. So it is a single variable problem and without constraint. So there is no constraint here, only we have that objective function and the problem is minimization type. The function here is f of x equal to x square plus 54 by x. So I would like to solve this problem using PSO, particle swarm optimization. So in MATLAB, so there is a function particle swarm. So this function can be used for solving an optimization problem using particle swarm optimization method. So here this is the function and these are the argument of this particular function. So what you have to do, we have to define the objective function, we have to define the number of variables, and then we have to define lower bound and we have to define upper bound, and there are some options we can define. So these are the arguments which is coming into this particular function, and from this particular function, so we will get the optimal value of this problem, or we will get the optimal solution, and we will also get the optimal function value. Okay. So here I have shown you the MATLAB code for solving this problem using particle swarm. So here these are the three lines, so which will clear the environment, and then I have defined the objective function just like we have defined in case of classical optimization technique, and then you define what is lower bound, what is upper bound. So in this case lower bound is 0, upper bound is 11, and then I have defined the options here. So you can define these optim options. So this is the function to define option, and here this is particle swarm, and this is the actually function I am using, particle swarm, and swarm size is 20. That means the population here is 20 I have defined here. So you can change it. So you can also define the other parameters of these particular algorithms here, and after that I have used this one. So I have already defined objective function, and number of variable here is your, this is n vars. Okay. So number of variables, so that is 1, and we have already defined lower bound, we have already defined upper bound, and we have defined options. And then if I execute this particular M file, then I will get the solution of this particular problem. Okay, optimal solution of this particular problem. And here you can see, so this is the MATLAB code, and if I execute this one using the run button, so then I will get the optimal solution of this problem. So I will show you in MATLAB how you can means run this particular code. So that I will show you. Before that, let me explain the other problem that I will be solving in today's class. The second problem is also a single variable optimization problem. So, we have only one variable, that is x, and the function is twice x cube minus thrice x square minus 12x plus 4, and lower bound is 0, upper bound is 8. So, this is the optimization code, and here what you have to define? You have to define the objective function, lower bound, upper bound, and then I am using particle swarm function to solve this problem using particle swarm optimization. So, this is the MATLAB code of this particular problem. Now, let us see a multivariable problem. So, we do not have any constraint here. So, we have only the objective function. So, here we have two variables, that is x and y, and the function is x square plus y minus 11 whole square plus x plus y square minus 7 whole square, and the range is between -3 and +3. Okay. So, value of the x is between -3 and +3, okay, and y is also between -3 and +3. Okay. And this is the function, this is the MATLAB code. So, here I am defining the objective function, and I am defining lower bound and upper bound. So, lower bound is -3, upper bound is 3, and then you are using particle swarm and you are defining objective function. Now, my variable is 2. Okay. So, variable is 2, and then you define lower bound, upper bound, and if you solve it, you will get the optimal value of this function. Now, let us see the next function, and this is also a two variable problem. That means, we have x and y, and the function is 10 plus x square minus 5 xy plus 9y square plus y, and range for x and y is -6 and +6, and this is the MATLAB code. Here I have defined the objective function, and here the lower bound is -6 and -6, and upper bound is 6, and then you are using particle swarm, okay, objective function, and here number of variable is again 2, lower bound and upper bound we have defined, and I can get the solution of this particular problem. Now, let us see a problem with constraint now. So, we have objective function, and there are three equality type constraints. So, this is equality type constraint, okay. So, type constraint, okay, and the range for x1, x2, x3, x4 and x5 is between -5 and +5, okay. So, this is a complicated problem. So, this problem we have solved using classical optimization method, and here we will solve this problem using particle swarm optimization. So, here what you have to do, we have constraint now, okay. So, we have constraint now. Now, in the objective function I am using the penalty approach. So, what I am doing here, so if the solution is feasible, then the fitness value, if I say here fitness value will be the objective function value, if the solution is feasible, if the solution is feasible, if the solution is feasible, then f equal to objective function value, else f equal to objective function plus I am using some penalty, okay. And that penalty I am putting it 10 to the power, it is a very high number, I am putting 10 to the power 185, okay. So, this number I am putting, and so because I would like to avoid this solution, the infeasible solution. So, how I am doing that? That you have written the objective function. So, this is objective function. Then calculate the value of first constraint, second constraint, third constraint. So, this is I have written 3 lines. So, the first one is first constraint, then second constraint, the third constraint. Now, I have used the if else statement here, and if so the constraint should be equal to 0, because C1 01 should be equal to 0, C02 equal to 0 and C03 equal to 0. So, I have used if else statement. So, if C 1 equal to 0 and I have used n, that means C02 equal to 0 and C03 equal to 0. Okay. So, in that case else f equal to objective function plus 10 to the power 185, that means it is a very huge number I am putting. So, let us see whether I will get this solution or not, and if you are, suppose sometime what may happen, you may not get the solution. So, sometime it may be difficult to satisfy this equality constraint. So, in that case what I will do, that C01, the absolute value of this one minus epsilon can be less than equal to 0. So, I can convert this equality constraint to an inequality constraint. So, therefore, if the absolute value of C01 is less than epsilon, so in that case it is fine. So, similarly I can convert the other equation, suppose C01 minus epsilon is less than equal to 0, then C02 minus epsilon less than equal to 0 and C03 minus epsilon less than equal to 0. So, we can convert this equality constraint to inequality constraint. So, here what we can do, we can actually allow some error. Okay. So, we can allow some error, and if the error is less than epsilon value, so in that case I can say that constraint has been satisfied. But in this case I have put that C1 equal to 0, C2 equal to 0 and C3 equal to 0. So, if the solution is feasible and if the solution is not feasible, so in that case this will be equal to very large number, and this is the MATLAB code, and once you are using this one, so you should get the solution of this particular problem. So, let us see another problem with constraint. So, in that case we have inequality constraint. The earlier problem we have equality constraint, but here we have inequality constraint. So, let us see this problem. So, here this is the objective function, that x1 square plus x2 minus 11 whole square, then x2 square plus x1 minus 7 whole square. So, here there are two constraints. The first one is that x1 minus 5 whole square plus x2 square less than equal to 26 and 4x1 plus x2 less than equal to 20, and both x1 and x2 are positive, and the range is that x1 and x2 are between 0 and 5. Okay. So, this is the solution, and what I have done here. So, here also I have defined the objective function. This is the objective function, and then this is constraint 1 and this is constraint 2. So, now in this case that this constraint should be less than equal to 0 and this is also less than equal to 0. If it is 0, that means the solution is feasible, then f equal to the objective function value, else f equal to objective function value plus a large number. So, I have calculated the fitness function using this function, okay, and after that I have used particle swarm, okay, and here this is the fitness function, and then we have two variable and lower bound and upper bound, and I have already defined what is lower bound and what is upper bound, and fitness function equal to objective function. So, that has been defined, and if you are executing this code, so you will get the solution of this problem. Now, let us look at another problem with constraint. So, the problem is that e to the power x1 into 4x1 square plus twice x2 square plus 4x1 x2 plus twice x2 plus 1. So, this is the objective function, this is the objective function, and we have two constraints. So, this is the first one and this is the second one, and then x1 and x2 are positive and it is between 0 and 5. Okay. So, unconstrained optimization solution is somewhere here. Okay. So, this is the contour plot of this particular objective function. So, somewhere here, and this is at but the constraint solution will be somewhere here. Okay. So, let us see the code here. Again I have written this fitness function or objective function here. This is the objective function, then these are two constraints, that is C01 and C02, and in this case the C01 and C02 both are less than equal to 0, less than equal to 0. So, if it is satisfied, that means the solution is feasible, then f equal to OF, or otherwise it is a large number in order to avoid that solution. And here I have defined the MATLAB code for solving this problem. So, here I have used optimization, and swarm size I have used 100, and I have also used hybridization. So, that also I will discuss. So, what will happen, sometime what happen when you are using PSO algorithm or GA. So, you may not get the exact optimal solution. Suppose I would like to solve this problem. So, PSO and GA. So, this is the actual solution of this problem, but PSO is giving a near optimal solution. So, somewhere here. So, what you can do, I can take whatever solution you are getting after PSO run. So, that solution I can take as initial solution, and I can refine using a classical method in order to get the exact optimal solution of this problem, and this method is known as hybrid optimization method. So, what we are doing, initially we are using some meta heuristic optimization method, and we are getting suppose a near optimal solution, and that near optimal solution we are taking as an initial solution, and then we apply the classical method, because in the classical method we are using the gradient information and we can find the exact optimal solution of the problem, and this is known as hybridization. So, here what you can do, that if you are writing that hybrid function, so that means this will go for hybrid method, and here I have written that hybrid function is f mean con. So, f mean con, okay. So, this is a classical method. So, what you are doing, so whatever solution you are getting using PSO, that solution will be used as a initial optimal solution, then f mean con will be used to get the actual solution. So, idea is that, so you have used PSO, okay, you got this particular solution, or you can say, and after that taking this initial solution you are using f mean con, okay, and you are getting the actual optimal solution, okay. So, you are getting the actual optimal solution. So, in this case I have used the hybrid method. So, otherwise if you are not writing this one, then hybrid method will not be used. So, you are only getting the solution obtained by the particle swarm optimization, and then you are using particle swarm optimization. So, you are writing fitness, the number of variable is 2, then lower bound, then upper bound, and then option, okay. So, I will also show you how you can solve this problem using hybrid method. So, now let us try and let us solve this problem using MATLAB, okay. So, I will use the online version of MATLAB, and let us see, I will solve the first problem to the last problem we have discussed using particle swarm optimization. So, let us take the first problem. So, this is the function. So, here you can see I have defined the objective function here, and these 3 lines just to clean the environment, and then I have defined the objective function, and then lower bound and upper bound, and then option I have defined. So, swarm size I have defined 20, and then I have used this particular line to run the particle swarm optimization. So, here what you have to define? You have to define the objective function, and then number of variable is 1, then lower bound, then upper bound, and then option. So, if you are running these few lines, so hardly you just see there are only 7 to 8 lines, and then if you execute this particular M file, so you will get the solution of this particular function. So, let us see. So, I got the solution. The solution is x equal to 3 and function value is 27. This problem also we have solved using the classical optimization methods, and you got the same solution, that is 3 and 27. Okay. Now, let us see the second one. The second one is this particular function, and let us solve this problem. So, here this is the objective function I have defined, and then lower bound and then upper bound, and then I have used PSO. So, here objective function number of variable is 1, lower bound and upper bound I have defined. So, if I execute this particular MATLAB code, then let us see, I will get the solution of this problem. So, here the x star is 2 and function value is minus 16. Okay. So, this is single variable optimization function. So, I got the solution that x equal to 2 and function value is minus 16. Now, let us see the third problem. So, this is a multivariable function. So, let us see this particular problem. So, let me copy these lines. So, I will paste it here. Here you just see I have defined the objective function. So, now I have two variables, that is x1 and x2. So, this x I have defined as a vector. So, here this is x1 square plus x2 minus 11 whole square, then x1 square plus x2 square minus 7 whole square, and then lower bound is minus 3, upper bound is plus 3, and then I have used this particular function particle swarm. So, let me execute this. I am getting, this is the solution 3, 2 and optimal function value is almost 0. So, I got the solution of this particular problem. So, if I change the range, so I can change it, suppose if I change it that minus 5 and minus 5, okay, then let us see what will happen. So, plus 5 and plus 5. So, if I run this particular function, so I am getting a different solution, but this is not an optimal solution. Objective function value is 193.12, but it should be 0. So, let me run this again. Now, I am getting a solution. You just see this is one of the solution and objective function value is almost 0. You can again try. Yeah, this time I am not getting, okay, this is not 0, this is not 0, this is not 0. So, I am not getting the solution. So, what I can do basically, so I can put the option, I can just see. So, here I am defining the option. So, what I will do, I will increase this swarm size, suppose I am using 50. So, what will happen, just see, if I am using 50, so I have to write option here, options, okay. So, I am writing and I am using swarm size, that means population size is 50 now. I am getting a solution 3, 2. You just see. So, by increasing population size, so if you are not getting solution, then you increase the population size, or you can also change the other parameters. So, that I am not discussing here, but you can also change the other parameters, but here I am changing the population size. Okay, I got the solution. So, let me try again. Yeah, I am getting another solution, and this is also a solution because this value is 0. Yeah. So, you just see you are getting solution. So, by increasing the population size, so you are getting one of the solutions. So, as you know, for this particular problem, we have 4 optimal solution, and they are alternate optimal solutions because objective function value is 0, but solution is different. So, we are getting one of that solution between minus 5 and plus 5. Or otherwise what I can do, I can also use the hybrid function, okay. So, that I can use. So, I can also use the hybrid function. So, let me copy this part. So, just see what will happen. So, here I am using the hybrid function. So, let me try with 20 solution now. Let us see whether I am getting a solution. Yeah, I am getting. So, you just see this is 3 2, an exact solution I am getting, and objective function value is almost 0. So, with 20 population. Let me try again. Yeah, I am getting. Yeah, let me try again. So, I am getting a solution. So, you just see I am getting a solution. So, in case of hybrid method, so what is happening that whatever solution you are getting from PSO, so that solution you are taking as an initial solution, and then you are refining your solution, or you are trying to get a better solution using the classical optimization method. Okay. So, this is your hybrid method we are using. So, let me try another function. So, let me try this particular function. So, maybe I can open a different file. Okay. So, this is the problem I would like to solve using particle swarm optimization. Okay. So, I am getting a solution. This is minus 0.4548 and minus 0.1819. So, I am not sure whether this is the solution. So, let me try again. Let me try again. Let me try again. Yeah. So, I am getting. So, I can also use hybrid method, just see whether you are getting a better solution or not. Okay. So, what I will do, I will put option here and I will write options. Okay. So, I am writing options here. Yeah. So, I think this is the solution of this particular problem, and objective function value is 9.9091. Okay. So, I got the solution of this particular problem. So, here what I have done, I have defined the objective function, then lower bound upper bound I have defined, then this is the option I have defined. So, here swarm size I have used 20, and I have used hybrid function, that is f min con I have used, and then I have used particle swarm optimization with these particular options. So, I am getting the solution of this problem. So, let me try the next problem. So, next problem is an optimization problem with constraints. So, we have 3 equality constraints. So, let me see. So, this is the MATLAB code. Let me copy this code and I will put it here. Okay. So, this is the code here. So, what I am doing, so I am just writing this objective function. So, this name of the function is ofun. So, this is the objective function, and first line is objective function value, and then this is constraint 1, constraint 2, constraint 3. Now, what I have done, if constraint 1 equal to 0, constraint 2 equal to 0 and constraint 3 equal to 0, that means that is a feasible solution. So, therefore, the fitness value equal to objective function value, else the fitness value is objective function value plus a large number, because the problem is a minimization type problem. So, therefore, I am using a large number. So, let me execute this. So, I am getting this particular solution. Let us go to the next problem. So, next problem is again this is a multivariable problem with 2 inequality constraints. So, let me copy this particular file. So, here so I have defined the lower bound, and I have also defined the upper bound, and then this particle swarm function is used, and then this is the objective function I have calculated. So, objective function, and there are 2 constraints. Now, in this case the constraint should be less than equal to 0. Okay. So, C01 is less than equal to 0 and C02 is less than equal to 0. So, if there is no violation, so in that case the objective function value is equal to fitness value, or otherwise there will be a violation. So, that we have used, and let me execute this particular M file. Yeah. So, I am getting a solution. You just see this is a solution, and let me see. So, I can change this lower bound and upper bound. So, between -5 and +5, yeah, I am getting 3 2. So, 3 2 is one of the solution. So, I am getting that one, and yeah, so I am getting another solution. So, this is I am getting the constraint optimal solution of the problem. Now, let me go to the another problem. So, this problem is there are again, this is a constraint optimization problem with two inequality constraint. Okay. So, this is the code, and here you can see. So, here again I have defined the objective function here. So, there are two constraints, that is C1, C01 and C02, and then we are calculating the value of f. So, if there is no violation, then this value is objective function value, or otherwise we are putting some big values. Okay. So, in order to avoid that particular solution. So, let me execute this one. Yeah. So, I am getting the solution of this particular problem. So, that is 0 and 1.500. So, in this case I have used the hybrid function. So, what is happening, that after PSO solution, so that solution has been used, and to and then fmin_con function is used, and to get a better solution of this particular problem. Now, let us see how we can solve this problem using genetic algorithm. Okay. So, here the genetic algorithm function is GA. Okay. So, I have to use this function, and this is the syntax of this particular function. So, here I can handle lot of things. So, this is the value of the objective function. Okay. So, objective function, then you are putting initial solution, then A and B. So, this is the inequality constraint. Okay. So, this is the inequality linear constraint. So, I can put just like fmin_con, I can put linear inequality constraint, and AEQ and BEQ, that is the linear equality constraint. So, this is linear inequality constraint and this is equality constraint, and I can also define the lower bound and upper bound, and here I can define the constraint if there is any nonlinear constraint. So, I can define here, and I can also give the option. Now, in option, if you are not giving, the default options will be taken, otherwise you can define your own option. So, one option may be, so this is optim option. So, this keyword is same. So, here earlier I have used particles from, but in this case it is GA. Then you are using selection function. So, selection function you are using tournament selection, and size of the tournament you can define that 2, 3, 4, whatever tournament size you can define. So, you can also define your own function. Okay. So, own function, that is my function. So, you can also define your own selection function. Suppose I am defining here. So, I am not discussing these things. So, this is little bit in this is an advanced topic. So, you can also define your own selection function here. So, this way I can define. So, I have defined here what is B and BEQ, that is their vector. This is also A and AEQ is matrix, and this CX and CEQX. So, these are the function. So, basically nonlinear constraint, then fx is objective function, and these are nonlinear function, and I can also define lower bound, upper bound here. Okay. So, let us see how we can solve a simple problem using GA. So, let us start with a single variable optimization problem, and that is x square plus 54 by x. So, I know the solution, that is here x equal to 3 and f value f3 equal to 27. So, I know the solution of this particular problem, and here I have written this M code. So, objective function is defined, then lower bound, upper bound, A, B, A equality, B equality. So, that has been defined, and nonlinear constraint we do not have, there is no constraint here, and so I did not define, then I have used this GF function. Okay. So, objective function then 1. Okay. So, this is, and I have written here, and if you are running this particular code, then you should get the solution of this problem, that is 3 and 27. Okay. That is 3 and 27. Now, let us see another problem. This problem is twice x cube plus thrice x square minus 12x plus 4, and this is between 0 and 8. Okay. And this is the code. So, I am writing the objective function, and this is I have defined. So, I do not have that I have defined lower bound and upper bound. A, B, A equality, B equality is not there, nonlinear constraint is not there. So, I am just defining this one. So, if I execute this one, I should get the solution of this particular problem. Now, this is a multivariable function. So, here you have defined the multivariable function, and I have defined lower bound and upper bound, and these are all not there. Okay. So, I am putting null, and then I am using the GA function. Okay. So, this is the code, and if you run it, so you should get the solution. So, I will show you that one. So, this is another problem. So, this is again multivariable problem without constraint. So, here I have defined the function, and then you apply this GA function to get the solution of this particular problem. Okay. So, this is the MATLAB code, and this is the constraint problem. So, we have 3 inequality constraints. So, the problem has already been defined. So, let me see how we can explain this problem in GA. So, in case of PSO, I cannot define the nonlinear constraint. So, therefore, I have written my own function for defining the nonlinear constraint, but here you can actually define the nonlinear constraint separately, just like your f min con. So, what I have done here, so this is the objective function, then this is the lower bound and upper bound, and these are all empty, and nonlinear constraint is your NL con. So, that is the nonlinear function. So, here I have defined the nonlinear function. So, this is the first constraint, this is the second constraint, and this is the third constraint, and all of them are equality constraint, and there is no inequality constraint. So, I am writing it null. Okay. So, this is similar to f min con, okay, function. Already I have defined these things in the last class. Okay. So, last class I have defined how you can use f min con. So, there also we have defined this constraint like this. So, I have written this MATLAB code here. So, I will also explain the MATLAB code when I will go to the MATLAB online. So, there I will show you, and if I execute this line, so I should get the solution of this problem. Now, this is another problem with 2 inequality constraints. So, this problem has already been defined, and this is the MATLAB code here. So, this is the objective function, then you are defining lower bound, and these are all empty. Then if you are using the GA function. Okay. So, here you have defined these 2 constraints. So, there is no equality constraint. So, that is empty. Okay. Null you are putting, and there are 2 inequality constraints C1 and C2. Okay. So, I have written the code here, and this is the last problem. So, here we have 2 inequality constraint with nonlinear objective function, and this is the nonlinear objective function I have defined, and then this is the con function, lower bound, upper bound, and this is the GA. So, here we have 2 inequality constraints. So, this is the first constraint, this is C1, and this is your second constraint, this is C2, and that is the second nonlinear constraint, and we do not have any inequality type constraint, and if you are running this one, then you should get the solution of this particular problem. So, let us go to MATLAB and just see. So, let me explain from here. So, let me solve the first problem using GA. So, this is the first problem, and I will put it here, and here we have only objective function and lower bound and upper bound. Okay. So, that means this part is not there. So, I can remove also. So, because this is not there and I have lower bound and upper bound. So, up to here and then I have defined lower bound, upper bound, then A equality, B equality I have defined and nonlinear constraint is not there. So, I can also remove this one. So, this is not there. Okay. So, these few lines are sufficient. So, I have defined the objective function and then I am using this particular GA function. So, here I have defined the objective function, number of variable is 1, then A equality, B equality is null, then lower bound and upper bound I have defined. Okay. So, let me run this particular M file. So, I am getting the solution, that is 3 2. So, what I can do, I can also put the null here. So, this is the empty matrix. So, I can empty matrix or vector I can put it and lower bound and upper bound I have defined. Okay. So, that means these particular things I can remove. Okay. Okay. So, I have defined lower bound and upper bound and then I am just executing this particular line. So, let me see whether I am getting the solution or not. Yes, I am getting the solution. Suppose if I am not putting anything, so what will happen? So, only I am defining objective function and number of variable, that is 1. Okay. So, I do not need these lines also. Let me see whether I am getting the solution of this particular problem. So, I am not getting. So, that means J is starting from your either 0 0 or somewhere. So, that is why I am not getting this one. So, I have to define the lower bound and upper bound. Okay. So, then only I will get the solution. But if you increase your population, so you may get the solution also. You can try that one, but otherwise you put the lower bound and upper bound to get the solution. Okay. Or otherwise you can increase your population size or you can also increase the number of iteration. So, you may get the solution. So, let me try the second function. So, this function I have defined here. So, let me copy and yeah. So, here I do not have any constraint. So, let me delete this part. Okay. So, I do not have this one. So, I am just deleting this part and I am defining A V A equality, B equality and lower bound and upper bound I have defined. Okay. So, this is not required. So, I have defined lower bound and upper bound. Lower bound is 0, upper bound is 8. Okay. So, let me run this particular M file. Yeah. So, I am getting Excel solution is 2 and 16. So, I am getting 1.999, but anyway let us see. So, I am getting 2 and 16. Okay. So, second time I am getting 2 and 16. So, this is the solution of this particular problem. So, this problem you can try without defining the lower bound, upper bound, just see. So, I am not getting that solution. So, I am getting a different solution here. So, let me try this next problem. So, this is a multivariable problem without constraint. So, this is a multivariable problem without constraint. So, I do not have constraint here. So, I can remove this part. So, this is not required and I am defining the A, B, A equality, B equality and lower bound and upper bound. So, this is I do not need this one. Okay. So, I do not need this one. So, I have defined the lower bound and upper bound. So, this is -3 -3 and +3 +3 +3 and this is the objective function. So, you need the objective function and you need the lower bound and upper bound. Okay. So, and number of variable is 2 in this case. So, let me see. Yes, I am getting one solution. Okay. So, this is between -3 and +3. Okay, then let me go to the next problem. So, this problem is again a multivariable problem. So, what I can do? Yeah, I can copy this part. So, I have defined the objective function and then lower bound and upper bound, that is, n number of variables are 2. Okay. So, let me execute this one. Yeah, I am getting a solution. Okay. So, this is the solution of this particular problem. So, second time also I am getting the same solution. So, now let me try a constraint problem. So, this is the constraint problem and this is the code of this particular, this is the code of this is the code to solve this particular problem. Okay. So, here you just see anyway. So, I would like to delete this part in order to reduce the number of lines. Okay. So, I am defining here, this is null, this is null, this is null, this is also empty. Okay. And this is integer value is not there and I can define that n con somewhere here itself. Okay. So, this is not required. Okay. And this is not okay. And then I have defined the constraint function here. So, we have 3 constraint. So, this is the first one, okay, this is the second one, this is the third one, and that C inequality constraints are not there. So, therefore, this is empty and I hope I have defined the problem here, and if you execute this particular M file. So, you should get the solution of this problem. So, let me see. So, I didn't. So, I can check what is the solution. Solution is, yeah. So, this is the solution of this particular problem. You can check. We have already solved this problem using classical method. So, you can also see actually what is the solution you got using classical method. So, this is, yeah. So, you are getting some different solution. Okay. So, you are not getting the same solution. So, then we have to see which one is the actual solution of this particular problem. So, if you are not getting the actual solution, then what you can do? You can use the hybrid method, okay, so to get the exact optimal solution of the problem. So, in this case you may not get the exact optimal solution of the problem because we are not using gradient information here. So, in that case you can use the hybrid method. Okay, then let me go to the next problem. So, next problem we have 2 inequality constraint. So, let me see that one. So, here I am defining here itself. So, we have nonlinear constraint, but this is not there. So, I am removing it. So, here you just see we do not have any equality constraint. So, this is empty and we have 2 inequality constraints. So, that I am putting C1 and C2. So, after that I am running this particular line in order to get the solution, and then solution your x and x value you will get, that the objective function value you will get at optimal solution, that you will get, and I have defined this problem. So, lower bound I have defined. So, lower bound is 0 and upper bound is 5 here. So, lower bound and upper bound is defined here, and so if I run this particular file, so I should get the solution of the problem. So, I am getting a constraint solution. Just see, this is one solution, this is another solution. Yeah, so you are getting the constraint solution of this particular problem. Let me execute this particular function. So, this is the third problem. So, third problem is, so we have two inequality constraint. So, here I have defined the objective function, then this is the nonlinear constraints. So, nonlinear constraints defined here. So, we have two constraints here. So, this is the first one and this is the second one, okay. And there is no equality type constraint, and lower bound and upper bound has been defined. Then after that, if you are executing this particular line, so you should get the solution of this particular problem. Yeah, so I am getting solution is 0 and 1.5. So, 0 and 1.5 is the solution, and you can see. So, I am getting the solution, okay, 0 and 1.59 I am getting, but this solution is 0 and 1.5, okay. Now, if you want to see how you can plot this function, so that I have already shown you, but let me show that one. So, if I, yeah, so this is the lines. So, if you are using this line, so you can plot the function. So, you can plot the function using these lines, okay. So, these lines actually. So, here you have to define the function, and then f source you are using. So, f source means you will get the surface. So, let me see the first surface, let me see, and then I will show you the contour, okay. So, let me show you the surface. Yeah, I got the solution, and you can see the surface here. Yeah, so this is the surface. So, you cannot see actually where is the optimal solution, this is quite flat. So, therefore, let me see the contour lines, okay. So, I can plot the contour and I can see where is the solution, okay. So, let me run it again. So, this time I will get the contours. Yeah. So, I am getting the solution is unconstrained solution is somewhere here, but constraint solution is 0 and 1.5. So, x is 0 and 1.5 is somewhere here, okay. So, this is 1.5 somewhere here, constraint solution of this particular problem. So, you can also plot. So, MATLAB is quite good in graphics. So, you can actually plot the surface, you can plot the contours, okay, and you can see actually where the optimum is there, okay, optimum solution is there, okay. So, thank you very much. So, in this class we have solved few problems using genetic algorithm and particle swarm optimization method. So, initially we have solved the problem using particle swarm optimization. So, this is particle swarm in MATLAB, and then we have solved the same problem using genetic algorithm. So, what you can do, in the last class we have solved this problem using classical method, and you can try to solve this problem using classical method as well as genetic algorithm or particle swarm optimization. Then you can feel the difference that some problem is quite easy to solve using classical method, but some problem which is basically a non-linear non-convex problem. So, if you have more than one optimal solution and one of them is the global optimal solution. So, in that case you may not get the global optimal solution using classical method. So, in that case you can get the global optimal solution of the problem using genetic algorithm. So, I have also mentioned one important point here, that when you are using particle sum optimization or genetic algorithm, so you may not get the exact optimal solution of the problem. So, because you are not using gradient information, so you may not get the global optimal solution of the problem, exact global optimal solution of the problem, but you may get a solution which is very near to the global optimal solution of the problem. So, this is not the actual optimal solution, but it is a near global optimal solution. So, then what you can do? You can use the hybrid method. So, what you will do? So, whatever solution you have got using genetic algorithm or PSO, so that solution you can take as an initial solution and you can apply your classical method. Okay. So, you will get the actual optimal solution of the problem. So, this method is known as hybrid optimization method, and this facility is also available in MATLAB. So, you can directly use the hybrid method to get the exact optimal solution of the problem. So, I want that you please solve this problem yourself and just see the difference when you are solving this problem using classical method as well as genetic algorithm. Thank you.